Okay, hello everyone. So, next Monday is exam 2, and it covers chapter 11 through 27. So, and you're going to be in slightly different locations, or some of you will be, so I'll post those shortly. But right now I want to first alert you that I moved the homework that's usually due on Wednesday till Friday so that it could cover everything, what we're doing today and what we do on Thursday. We'll finish up everything today. We'll just have one chapter left for Thursday, and then we'll do a review for the exam. But the conflict exam sign up is now posted, and it's due on Friday. So it's posted now. So if you want to take the conflict at 4:30, you feel free to do that. Just sign up before Friday at midnight. So that's pretty much, and I posted the exam practice on, you get a practice exam on Lon Kappa for each exam, so I've posted that already, so you can try the exam practice in your notebook and online. And the one online has new variations, multiple randomizations, so you can try it over and over again with different numbers, which will be helpful for some of the problems in exam 2 because there's a lot of calculations for some of them. So let's see what else. So today, let's just see how far we get. And we left off here. Let's just look over here at the document camera. And we left off here on page 117. So we were doing these calculations for these 9 points. And you had for homework this experiment too. So you probably all know how to do this. We didn't quite finish it in lecture. I posted it online, but we can quickly fill it in here on our notes in case you didn't look online. All right, so what have we done so far? We've calculated these sum of squares total between and within, and we got 42 for the model. This is 1.5 for the error and 43.5 total. And, of course, 42 plus 1.5 has to sum to 43.5. Now, the degrees of freedom here, and these are the usual, n minus 1, and n is the number of observations. We have 9. 9 minus 1 is 8, so that goes here. And then the degrees of freedom for the model, that's always the number of parameters minus 1. And in this case, the parameters is the number of groups we have. We have 3 groups, group A, group B, and group C, in our model. Our model is, remember, predicting, for overall, it's predicting, it has these 3 parameters, these 3 group means we're making predictions based off of. So it's 3 minus 1, so that's 2, and then they have to sum up to 8 here. And this is n minus the number of parameters, 9 minus 3. There's 3 groups, 3 parameters. There, I have it written there. Okay? And so then what we just do, we do the usual, 42 divided by 2, and we get 21 here. 1.5 divided by 6, and we get 0.25 here. We don't do that. We don't need to. And now F is just the ratio of 21 over 0.25, and we get, divided by that, we get 84. Now that should jump out at you as a huge F. Remember, when the null is true, the null means that there's no difference in means between these two. These 2 groups are essentially the same, right? We'll do just as well if we predict the mean response, which would be 0 for everybody, no matter what group they're in. And that's clearly not true. And so we get this, if the null was true, we'd expect to get what? We'd expect to get an F stat of about 1, right? That's what so we could, when the null is true, getting something like 84 is just such an extreme statistic. It could happen, but it's extremely, extremely unlikely. And so it's going to have a very small p-value. All right? And so, so we could look to get the exact p-value. We'd look on a table, an F table, with the number of degrees of freedom, 2 for the numerator and 6 for the denominator. All right, and we'd see that that's much further out than the critical values for F. All right, so then the SD, what is this? This is a measure of basically the spread of the errors. So it's just a slightly adjusted standard deviation of the errors, and it's just the square root of the mean square. It's the root mean square here, and that's 0.5. All right, and then to get the R squared, how do we get the R squared? Well, remember, the R squared is what? The proportion of the variability that's due to the model. So it's 42 over 43.5. That's a very high R squared. Look how much of the variability of the y's is explained by the model. It's a huge percentage. And remember what we're doing here. This is SST, right? And we're breaking it up into two parts. The part that's explained by the model, which is R squared times SST, and the part that's left in the errors, which is 1 minus R squared times SST. So you can see, if you solve for R squared here, it's SS, this is, you have SS model equals R squared over SST, so R squared is the sum of squares model over the sum of squares total. Okay? So I think that's pretty much it, and then you did this one. And now what we're going to do, so our next example is just looking at survey data, but why don't we look at our own survey data and do an iClicker on the same question. So let's go to our PC here, and let's go to our own survey data here. And this was let's look at our last survey. And let's look at your answers. Okay, Stat 200. This is the last survey you filled out. And so one of the questions, we can do a very similar question to what appears on 118, but just with our group, what appears on page 118. So you answered this question. Do you favor or oppose allowing gays and lesbians to marry legally? On a scale of 0 to 10, rate where you fall. So 0 means you strongly favor gay marriage, and 10 means you strongly oppose it. So where did this class fall? So let's look at our data. And first, just let's look at a histogram of this. And let's adjust the bin so that we can see. I want 11 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, because there are 11 possibilities. All right, so you can see that about, this was the overwhelming answer, about 38% of you responded that you're completely in favor of gay marriage, but then there's a spike right here at 5, right in the middle, and then there's more people said 10 than said 9. These look about even, and here's our statistics. So the average response was 2.459, the median was 1, and it ranged from 0 to 10, and 231 people responded, 200 people. So now I'm going to ask you an iClicker question to predict, do you think you can make a better, so the null says that we have to pick some groups. So I'm going to pick ethnicity for this class. And we'll see, based on your ethnicity, do you think we can make a better prediction for what your opinions are, this quantitative variable from 0 to 10, what your opinions are on this question? Do you think using your ethnicity, your group membership, is going to make a better prediction than just using the average here. That's what we're doing here with ANOVA. So what are the ethnicities that I asked? Let's see. The ethnicities. The ethnicity, well, I can tell you. Let's do an iClicker question what they are. So I want you to, first of all, guess. Where's our iClicker questions? All right, so I'm going to start this. I just want you to guess, just give a good estimate. Do you think, I just want you to, you can't get it right or wrong. I just want you to imagine which group do you think is most opposed to gay marriage. In this class, there weren't enough of the other ethnicities to protect privacy, so I just grouped everybody who wasn't, who's black, Hispanic, or other, who wasn't either East Asian, which is, China, Japan, and I included, Vietnam, Thailand, etc., or South Asian, which was India and Pakistan, and I put Indonesia there, too, or white or other. Sorry about the others, I had to do that, because otherwise, if there weren't enough of them, we could tell it wouldn't protect people's privacy. So I grouped them together. So just guess, who do you think is most opposed to gay marriage? And then we'll look at our data and see if you think it's significant. And then we'll do the example in the book. Okay. So we'll stop it. Whoa. So here we'll stop it. And let's see what you chose here. So you thought South Asians would be most. The Indians, maybe because of the Muslim, because Pakistanis are Muslim. I'm not sure why. Indonesians, a lot of Indonesians are Muslim. Maybe that's why you thought that. Anyway, so let's see. Let's look at the results here and see if you're right or wrong. Okay, so what we have to do now is to go, let's escape here. Get out of here. Whoops, I don't want to do that. Why did I do that? Sorry, I'm trying to escape from there. Okay. So let's look, and this will be fun. So we'll choose the split, and we'll split on ethnicity. And then we'll look at the split plots. And let's put the average and the median here. And here's the statistics. So it's East Asians. South Asians are the least opposed. You were completely wrong, the people who answered that. South Asians are most in favor of gay marriage. There are only 27 of them. East Asians are 133, but they were by far the most opposed. Then whites are the pretty, So you can see, looking at these, and we can look at the box plots, too. See, the median is right at 0 for whites. And for other, too. Maybe box plots look better. Let's try those. And you can see from the box plots that the red lines are the medians. So the medians for white is 0 and for South Asians is 1, but they have a lower average, South Asians. And why was that again? Let's check out the histogram. I'm curious about this. Oh yeah, look, South Asians, look, the cutoff is 5 here. Nobody opposed it more than 5, and look at, whites went all the way up to 10. So the average is pulled in the direction of the average is pulled down there, even though the median is 0. So half, and the median here is 1. So those are our stats, and do you think it would be significant? So do you think it's significant? Do you think, just guessing, does that look significant to you? It looks like significant differences to me, doesn't it? So we can do a test on that, and we can do it with our data program, and then we'll see how we do it. We'll do it by hand. All right, with different data. All right, so what would we do? We could go here, and we can go to multi-sample inference, because think of it as more than 2 samples. You can think of it as 4 groups, like 4 samples. We're looking at the differences between 4 groups. So we can't do a two-sample t-test or z-test. So we have to, so you can think of it as a multi-sample inference. You could also think of it as regression with a factor variable. But let's just look at this multi-sample. All right, we're going to choose the variable that we want, and that's gay marriage. And here, the p-value is extremely significant. If we did an f-test here, what would we get? The degrees, group degrees of freedom, the error degrees of freedom. Number of groups is 4, so the degrees of freedom is 3, right? And here are our averages. So after we see that it's overall significant, this is just the way that this is an overall test for significance. We can compare it with the chi-squared. And we get a slightly bigger p-value right here with the f and t as usual. And here's our r, 0.2364. That's our multiple correlation coefficient. So if we did r squared divided by 1 minus r squared, right, and then adjust it by these degrees of freedom, the ratio of these degrees of freedom, we are going to get this f-stat. And where this p-value comes from is looking, now you know that the f-stat is going to be about 1, right, when the null is true. And we've got an f-stat much bigger than that. So that's the idea. And so where we're headed this hour is, okay, once we do this overall regression, once we do this overall test, what's our next step? What would you be interested in? Remember what the null says is that all the group means are the same in the population, that just in our sample, they're not. And then the alternative says, no, at least one of these is different. Or we could say at least one of these pairs is different. Like, which pair do you think would be most significant? They're not all going to be different from each other, right? Like, look at these two. Whites and South Asians look very similar. But when we reject the null by this small p-value, we're saying at least there's at least one of these groups is different. Another way to look at it, what we're going to look at is which pairs are different. How many pairs are there? You could compare whites to Asians, South Asians, and others, right? And then you could compare if we're just doing pairwise comparisons, there's going to be 4 times 3 comparisons. And if we don't care about the direction, it will be 4 times 3 divided by 2. So which of these, I can show them to you, which of these, there's 6 of them, if we don't care about the direction, which ones do you think are significant? So then we're going to be doing these t-tests to see which of the pairs are significant. And as you can see here, this is doing confidence intervals. Let's do tests. You can see which ones are significant. White minus East Asian is significant at the 5% level. What happened to this one? East Asian minus South Asian. That has the biggest difference in average, because South Asians are most in favor of gay marriage, and East Asians are least in favor of gay marriage, most opposed. So they've got the biggest difference, but they're not as significant. That's because the sample sizes are smaller. So we have to factor that in. So that's what we're going to learn today. Okay? So there it is on the printout. We're going to do all this by hand. And so you'll understand it better. Any questions? You want to see anything else while we're here? Any other difference in attitudes on any other question when we're here? Here if anybody wants to see anything. How about, why don't we see if people have had a same-sex experience? Maybe that correlates with being gay. Not being gay, of course it correlates with being gay somewhat, right? If you've had, not necessarily, same sex, I suppose, could be with yourself, right? You are the same sex, but as yourself, right? I don't know. I shouldn't have worded it that way, but I meant with someone else. Okay. So let's look. And we can just look at that question too while we're here. So let's go to Well, I'm not going to do it unless you want to. Do you want to look at this, or do you want to just get on with the lecture? Raise your hand if you want to get on with the lecture. Raise your hand if you want to look at this. Okay, we'll look at it. So we'll just look at the histograms and box plots. And this time we're just going to look at same-sex experience instead of the other one. I got to erase the other one. Well, box plots, this just means that all the quartiles are 0 here. Let's look at the histograms. That will give us a better picture. That's still pretty bad. Let's look at the, it's just because yes or no. It's just a yes or no question, right? So let's look at the statistics. Okay, so what does this say? That 13% of whites have had a same-sex experience, 12% of East Asians, 11% of South Asian, and 14% of other. That's high. Don't you think that's pretty high? I'm going to split on gender. I'm more interested in that now. So let's just choose a split on gender and see how different that is. And let's look at the statistics. And so it says 13% of females versus 12.9 of males. All right. So that's interesting. So we could do, since it's a yes-no response, we really should do something called, we really shouldn't be using ANOVA for it, because this is a good example. Because ANOVA is used when you have a quantitative response, not just a yes-no response. Right? So we could do a chi-square test for independence here, is whether you are, like you did in Stat 100, is whether or not you have had a same-sex experience independent of your ethnicity. In other words, knowing your ethnicity, does that help you? Or knowing you could do a 2-sample Z for the gender. But we wouldn't be using ANOVA here. I'm very glad this came up. We wouldn't be using ANOVA here because we're not predicting a difference in the Y variable that we're trying to predict is not quantitative. It's just a 0-1 variable. So this would just be a chi-square test for independence. Or a 2-sample for this one. It's just a 2-sample Z-test. Just comparing males and females. Okay? All right. Let's go back to the notes. And so now we're going to do the same thing from, this was Stat 100 data, this same question on gay marriage. So in 2014, 858, we're on page 118, 858 students answered this question. On a scale of 0 to 10, where do you fall? And here's the 5 histograms, and here's the average for them. And so in Stat 100, much larger sample size, so I could break it down. I could have black and Hispanic, and there weren't as many. I just put all the Asians together, and mixed or other. Okay, so looking at this, what do you see? Did you see this is the highest, that jumps out at you, and this is the lowest, right? So the question is, are there differences between ethnic groups based on their attitudes to gay marriage in some wider population, right? And it looks like there's substantial differences, just like it did in our sample. So the idea is, can we predict a random person's attitude towards gay marriage better by using their group averages than we can by using the overall average of 2.577 for everyone, regardless of ethnicity? And so the correlation between the predicted ratings made based on ethnic group and the actual ratings that they gave is this R, 0.1920. I think ours was bigger for this class. That's a fairly low, looks fairly low, but is it big enough to be significant? So that's all we're doing. So let's just look at this. So we're testing the overall. We're not looking at pairwise comparisons. We're just looking at the overall. So what's the appropriate significance test? See if you can just circle one and see if you know it. I didn't put it on as an eye clicker because there's too many options. But what do you think is the appropriate significance test to test and know that all 5 of the group means are the same in the population? We just happen to see these small differences in our sample due to the luck of the draw. So you can eliminate the Z and the T. We can never use those for overall tests of significance, right? When we have multiple groups or multiple slopes. So that eliminates that. Now, you can use either of these two. The F is slightly more precise, and most people use that, but you could also use the chi-square. So you could use, oh, but that says only. No, Ellen, don't make that mistake on the test. So it's either, so our answer is either 1 or 2. Okay, does that make sense to everybody? Now, what's the alternative hypothesis? That all 5 group means are different than each other in the population? No. It just means the alternative is at least one of them. That's all. So now we're going to compute the chi-square statistic. So let's do that. That's super easy. The chi-square statistics is just r squared over 1 minus r squared times what? Do you remember? Just times n. So this is super easy. So you just say 0.1920 squared over 1 minus 0.1920 squared, and then times, there's a big, big sample size. So that's what's going to make it significant. It's going to give it a big chi-squared because of this huge sample size of 858. And I did that, and I got 32.84, and that should jump out at you. Because remember, the chi-square, when the null is true, we'd expect not 1, but we'd expect what? The degrees of freedom. So how many degrees of freedom are there? Let's do this one as an eye clicker. So see if you would know how many degrees of freedom is there. So let's just look at that. And here it is. So let's start that right here. Okay, so I'm not going to waste a lot more time on this. Why don't we just stop it at 35? Just choose one. Okay, let's see what you answered. Okay, so you're torn between these two. All right, so what's the answer here? The answer is this beat out. The answer is A, 4. Okay, so that's the answer, and let's look at the, let's write that down. So let's go over to the document camera, and the degrees of freedom for the chi-squared is always equal to nothing to do with n, it's the number of parameters minus 1. Okay, so in this case, I'll just write it's the number of parameters minus 1. So in this case, it's number of parameters is the number of groups here minus 1. So it's what? 5 minus 1, which is 4. All right? You don't tweak. It's like a Z. You don't have degrees of freedom based on sample size. How can you think about it? When you have infinite n, as n gets larger and larger and larger, the you know how the t becomes like the z distribution. Well, the f becomes like the chi-squared in the limit. So this doesn't. The degrees of freedom. You don't look at different curves for depending on sample size for chi-squared. You look at different curves depending on how many parameters you have, because the more parameters you have, you know, the more groups you have, the more likely you will be to get a higher r squared. Okay? So let's see. All right, so compute, so what do we have to do? So you found out that, how many degrees of, looking at the chi-square table, what's the critical value? Okay, so you can do this. Let's just look up at the back. So you're going to look at, these degrees of freedom refer to the number of parameters, and they correspond to different curves, different chi-square curves. So you look at your chi-square table, which is in the back of the book here, on page 257, and you're going to be looking at it with degrees of freedom 4 here. So you look, and so this is saying the critical value, these different critical values. If we want to use the usual 5% cutoff, this says that we, even though that we need at least a 9.49 chi-square stat. We have much bigger than that. What did we get? 30-something. So we certainly have a p-value smaller than 5%. Ours is way, 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 way out here somewhere. It's a tiny, tiny p-value. It's less than 0.1%. Do you understand? And this one is centered at about 4. This one looks like about the right distribution. This one looks like it's centered at about 4, the degrees of freedom. Okay? So let's write that down. So looking at what's the critical value at, so the critical value, so that's the star value, with a chi-square curve with 4 degrees of freedom is 9.49. This is at alpha equals 0.05. And the chi-square critical value with 4 degrees of freedom is equal to, at 0.1%, is equal to 18.47. Okay, so at that's 0.1%, 0.1%, and this is 5%. So what can we conclude? This is 0.1%. So what can we conclude? The conclusion is what? That at least one of those groups is different than the others, right? So we're going to reject the null. What do you conclude? We'll reject the null. So we reject null and conclude that at least one, the alternative is at least one of the groups is different. Then we'll look at which ones, okay? We'll do pairwise comparisons to look at each one. How about if we wanted to do the F statistic? It's very similar. So the F is going to, this part's going to be the same. The R squared over 1 minus R squared. That's the core signal to noise ratio. And then and then instead we tweak this n a little bit. We say n minus the number of parameters, n minus g. And then we also have this other set of degrees of freedom. This is like what this g minus 1, which the purpose of this is it centers f at its degrees at 1. This one doesn't have that. That's the difference. So this is centered at g minus 1. The mean, the expected value for chi-squared is the number, is its degrees of freedom. And this is centered at 1, because we're dividing by its degrees of freedom. Okay? And so let's do that. We get 0.1920 squared over 1 minus 0.1920 squared. And then we're going to multiply it by not 898, not 858, but what do you think? 853. We're subtracting off 5, because it's 5 groups. And then we're dividing it by 4. And when I do this, I got 8.16. Now, how many degrees of freedom? So this is our stat. You can compare them and see how the basic, they look very much this. They don't look, they're never going to look the same, because this one's going to be divided by the degrees. If you divide this one by its degrees of freedom, it's very close to that one. okay? Because this one is that's just the convention. This is centered, the expected values at its degrees of freedom, this one's centered at 1. I kind of like that. I like the F for that reason. Okay, so now let's go to the, we're going to answer the, well, how many degrees of freedom for F's numerator? I think you know that just looking at this. This should be a super easy iClicker. And let's just do it. And how many degrees, whoops. All right. You know this one, right? Look, we do it in the calculation. Remember, the numerator is how many, it corresponds to the parameters in the model. Numerator. Don't look at the simplified version. Think about the numerator is the model. So how many degrees of freedom are in the model? That's what you want. Okay, I'm going to stop it right now. And I hope you got this one right. The answer is 4. Yay, more people got it right, yes. Okay, and let's see if we have another. We'll go over that in a second. Let me see if there's another iClicker I put down here. Okay, how about let's do the denominator. Now you should get this one. I'm going to close it off at 30. Stop it at 30. Everybody should get this one right? Yay, good job. All right, so now let's go over to the document camera and fill this in. All right, so the degrees of freedom, if you got confused, remember we're simplifying this. This can also be written as what? This is the same thing as, I'll just write it here, F is equal to R squared divided by G minus 1. And this is 1 minus R squared, that divided by N minus G. When we simplify it, we get that. So this is for the numerator, and that's for the denominator, okay? So that's how you should think about it. And here we've got 4, and here we have 853. So looking at the F table, what's the critical value at 5%? Well, these F tables, you have 2 sets of degrees of freedom. That's going to make any F table super long, and we're not going to, this one doesn't go up that far for the degrees of error, degrees of freedom. So we'd have to look online for this. And so I already did, and I said the critical value for the curve that has 4 degrees of freedom in the numerator and 853 in the denominator is 2.382. And look at RF. It's way further out. Okay, it's way further out. If we drew the picture, F is only positive, right? So it looks something like, I don't know, it would go way out there. And here, the critical value is, it's centered at 1. This is like the critical, maybe here, this would be like, well, I drew it really badly, but this is like, this is the 5% mark. So this is 2.382, means that there's 5% here. That's 5%. And our chi-square statistic, our F, is way, sorry, I'm drawing this, it's way further out. It's, I didn't draw it very well, but it's, this is this one, right there. That's the 5% mark. So ours is off the page. So it has a very tiny p. Okay? Does that make sense? All right. This is at alpha equals 0.05. Just quick, why don't we just look at this since I drew that so poorly, you have a bad feel for it. Let's just look at it here. So we're going to look at it, get rid of all this, and let's just go to our p-value calculator for the F distribution, and we have 4 and 853. And then our p-value our F value, our F ratio, sorry, is 816. So what p-value do we get? So it's just out of range. It's so small. If we put in 5%, and there's where the 2.382. That's what it looks like. We just can't see it. It's so small. Okay? So we'll reject the null. Does that make sense? All right. So what do you conclude? We reject the null again. Any questions on that? Why do they even do this left-hand tail? What does that even mean? That means that how would you get, so that means that you're faking your data. People fake their data all the time. That's a test to see if people are faking their data. That means that the groups are so much alike each other that just by random chance it would be so unlikely that somebody's deliberately, because people have no sense of random variation, are deliberately trying to fake the data and make the groups look very much alike. So that's the test you do to guard against people if you think that people are not doing the experiment properly. Because it's very unlikely if you were doing it correctly to get that. Does that make sense? Okay. So let's go back to the document camera. And let's just, what do you conclude? Same as, that we'll reject the null and conclude overwhelming evidence that at least one of the group pairs are different. One of the groups is different than the others. Okay? So that's the idea. And now, let's see what else we can do here. So this is just our summary. And basically, to test, this is just the summary of chapter 24, to test all the group means at once to see if there's any difference. There's two ways we can do it. If we wanted to do it from scratch, you use this ANOVA table, but once you're given R squared, which you usually are, when you're given this table, you could use that you could do it that way. Okay? But the idea behind it, when you do it from scratch, is what? So this is your sum of squares total, which means what? This is just the sum from I equals 1 to n of what? Of every single one of your y's, like we had 858, minus the overall average for all those y's in our example, which was 2 point something, the overall average gay marriage rating. So that's what that is, and then we break it up into two pieces. We break it up into the sum of squares for the model, and that is from I equals 1 to n. What do? You take each one of those 858 students, and you take their predicted based on their group membership. So if they're whites, they would be predicted to have the white average. If they're blacks, the black average, etc. Minus, that's how better the model is versus just guessing the overall average. So these, for each one of them, there's basically just five. There's 5 predictions because there's 5 groups. For each one, you would subtract off the average. But then you have to do it for all 858 people. So if there's 2, however many there were in, let's say there were 300 whites, for each 300, one of them, you'd have the same prediction minus the same overall average. So that's that. And then this one is, what's this? This is your errors. So your errors are always what? Your observed minus your predicted, what the actual rating that each 858 of the people gave, minus each one of their predictions. So that's what that is. So it's for all from I equals 1 to 858, all for every single person, they have an actual and they have a predicted. And then you have to square each one of these. If you didn't square them, just sum them up, these would add to 0 if you didn't square them. These would sum to 0, and these would sum to 0. You just have 0, 0, and 0. Because there'd be positives and negatives, and they all cancel out. So that's what would happen if you didn't square them before you added them up. All right, and then these are like the sums, and then for each one you have to divide by we want the mean, right? This is the sum, so divide however many there are. Well, there's 5 groups. We don't divide by 5 because one of them we already basically have estimated already. If you know 4 of the group averages, you know the last one's determined once you know the overall average. So that's the idea here. And then you get this ratio, and that's it. Okay, so here we have, maybe I should color code these so you remember, because so many people got this wrong. This is for the numerator. It just ends up down here when we simplify it. This is for the denominator. It just ends up on the numerator here when we simplify it, okay? Now, you can see you get the same exact thing. Oh, why is this true? We just said it, we could say it again. Why is this true right here? Because sum of squares, this right here is r squared times SST. That's what that's equal to. So if you solve for r squared times SST is equal to SSB. So there. So r squared is SSB divided by SST. All right. So this, of course, is 1 minus r squared. So this is, if you're given r squared, then this is the super easy way to do it. All right? And if you're given r squared, then the chi-squared, super easy. So when the null is true, the f-stat is about 1. If you want to get really careful about it, it wouldn't be exactly 1. In this case, it would be what? 853 over 851, the degrees of freedom minus 2. So it's a little tiny bit bigger than 1. And when the null is true, the mean of the chi-squared is its degrees of freedom. Okay? And this, you don't have a lot to remember because this is, as I said in the video, if you didn't get a chance to watch the video, I filmed it right after class because I ran out of time last lecture. So I added a little bit to it and explained why the number of parameters is the number of groups, because really what we're doing here is a special case of regression based on group membership. You can write it as a linear model with factor variables. That's exactly what, if you're in the R-independent study, that's exactly what you did with the Chick-Weight problem. All right, you wrote it as a linear model with an intercept and then means to predict the different, well, you know what, it was an example of that. All right, so this is super important. The number of parameters is the number of groups, and it's really easy to see that. Just think of it as a linear model predicting this quantitative variable based on what group you're in. So there's however many groups, those are the parameters we're trying to estimate. We're using our sample group means to estimate the population group means. We're making there's 5 estimates for the 5 means, and you subtract 1 off for the degrees of freedom. It's exactly like what we ddid before with regression. Okay, any questions? So now we're just going to do these pairwise comparisons. And there's really, these are kind of fun to see, now we're going to see which groups are significant. We know once this chi-squared F tests tell us that at least one of the groups is different from the others, how can we determine which ones? Well, we can do our usual Z or T test between pairs of groups. It's like two sample t-tests or z-tests to see which is significant. All right, now they're called post-hoc comparisons because post-hoc means after this. So post-hoc, after this, after what? After you already looked at the data. So this means after looking at the data. So we look at the data, we look at all the means, and then we have to make an adjustment for these multiple post-hoc comparisons. First of all, why? Well, so let's just look at what we're doing here. Okay, so we saw this overall significance test. We got this huge F. We know there's something there. And now we look at these averages. We see, okay, well, the blacks are most opposed to gay marriage here, and the Hispanics are least opposed to gay marriage. So maybe that's the group we want to look at right there. We're not really interested in looking at Hispanic versus mixed and others because they don't look very significant to me. Or between blacks and Asians because they both look pretty opposed to gay marriage. They look pretty similar. So I wouldn't be interested in that. So I'm looking at the data. This is a post hoc. And now I'm going to pick out, which one do I want to look at? And do a significance test on. And I'd look at this and I'd probably say either maybe I'd like to look at blacks and Hispanics. That's the biggest, and they have the biggest difference between each other. All right, or even, and that's called a post hoc. See, because I'm picking out of all the possible differences, I'm cherry picking out one that's most significant. So think if you had tons and tons of groups, if you have 100 comparisons, 100 pairwise comparisons, and then I look them over, all 100 of them, and I pick out the biggest ones, the ones that I think are the biggest difference. Well, let's say I pick out 5 of them. Well, that's 5% of the 100. And just by the luck of the draw, if we're talking about p-values, if none of them were different from each other, 5 of them would appear significant at the 5% level by definition. So if you have multiple comparisons, you have to adjust for that if you don't specify your particular hypothesis of which pair you think is going to be significant ahead of time. Does that make sense to people? For example, it's the same problem that we talk about a lot. If you run multiple tests, if I did the same experiment 100 times, I don't get significance, I do the same experiment over and over and over and over and over. Well, just by definition, if I did it 100 times, about 5% of the time I would get significance. Because that's what it means. That when the null is true, when nothing's going on, just by random variation, you're going to get such an extreme difference 5% of the time. So if we run multiple tests, we have to adjust for that. That's the idea that we're going to do. But before we even get to that, here's the computer printout, and here is the ANOVA table. So I said, okay, I want to start. Well, first of all, we have to say how many possible unordered pairwise comparisons are there with G groups. Okay. Are there with 5 groups? So how would we do this? So for 5 groups, how many comparisons are there? Well, I could compare whites to 4 others. So that's 5, right? And then 4 others. And then I could compare blacks to 4 other groups. I could compare Hispanics to 4 other groups. So for each one of them, you could say, okay, whites is 4 other groups, 4. And then blacks, 4 other groups, plus 4, plus 4, plus 4, plus 4. That's 5 times 4 comparisons. But I said unordered because when I do that, and I compare whites to blacks, I count that as one. And then when I start with blacks and compare blacks to whites, that's another one. So I'd want to divide by 2 because I don't care if I don't, how many unordered pairs are there, if I don't want to distinguish. So there's 5. So for G equals 5, you'd have 5 times 4, and then you have to divide by 2. So that would be 20 divided by 2, and that's 10 pairwise comparisons. In general, you can see that for just G groups, it's just going to be G times G minus 1 divided by 2. That's how many pairwise comparisons, because you can compare each group to G minus 1 groups. And since there's G groups would be G times G minus 1, but then you divide by 2. So as you can see, when we do that, here they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's how many pairwise comparisons that there are. And that's what we're going to have to multiply our p-value by at the end to adjust for these post-hoc comparisons. But meanwhile, let's start by comparing, let's just say, okay, what are we going to do here? We look and we see these averages, and we see the blacks are the highest here, most opposed, and the Hispanics are the least opposed. So I want to look at that difference. Okay? I'm just curious, is that significant? So you state the null and the alternative hypothesis, and the null is what? The usual. The null is that in the population, the average, mu, the mean of the blacks, is equal to the average of the Hispanics. There's no difference in means, in population means, in this idealized larger population between blacks and Hispanics. All right, and what's the alternative? That they are different, but we don't specify a direction here because we're looking at unordered pairs. Okay, we're just looking at differences. So there is some difference, and that's why we saw such a big difference in our sample. So we're going to calculate a t-statistic. So our usual t-statistic, we could do a z, but it's just not usually done. We'll just stick to the t's. The t would be what? It would just be our observed difference between the two sample means minus the expected difference under the null. The observed difference, so it would be x bar or y bar for the blacks minus the Hispanics, this difference, minus the expected difference, which is just 0, over our standard error for the difference. Now, what is our standard error for the difference? Well, the observed difference we can get really easily. It's 3.643 minus 1.848, that, which is what? 1.795. And now we just have to get the standard error for the difference. So remember, a standard error for the difference, we know that it's the square root of the sum of two squares, right? It's going to be the square root of the standard error for one sample plus the standard error for the other sample squared. So what are we going to put in here? Remember what the standard error for an average is. The standard error for an average is SD over the square root of n. Well, so we know it's going to be SD over the square root of n. SD plus, right? Because we're doing the standard error, we're doing the t-test. So it's going to be SD plus over the square root of n. All right, well, we don't have any SDs here. We don't have any SDs here. And we're actually going to use not the SDs of our sample, but we're going to be using the standard deviation of the spread of all the observations. Why? Because remember, one of the assumptions for doing analysis of variance or doing any of these, for doing the F-test, is equal variability, right, across all the x's. Well, our x's is group membership, so we should have equal variability. Well, we do have these standard deviations here. I'm sorry, we could have used these, but why don't we use these? Because the assumption is, right here, the assumption is that these are the same. We have homoscedasticity, and so we can make a better estimate of these since they're all the same under the null. Under the null, they're all the same, right? We just happen to see these differences in our sample. So we're going to use our best estimate of the standard deviation of them all, which is this right here, our standard deviation of the errors plus. So this right here is what you use, and it's called a pooled estimate. So you use this pooled estimate that comes from all our observations. So it's a much better estimate. Pooled estimate of the standard deviation plus of the errors. That's what this is. It's a pooled estimate. As our best estimate of the standard deviation for each group. Okay, we'll call it the standard deviation plus. So that's what we're going to use. So remember, this is SD. We're talking about means here, difference of means. So here's how much is each time you sample. The mean for the blacks is going to jump around, and the mean for the Hispanics will move around. We don't expect exactly that or exactly that, right? It's going to vary, and the typical variation is SD over square root of n, like we always do for an average. So we're going to use SD plus over, we're going to use this pooled estimate. It's super easy, 3.18 for both of these. But now we do have to adjust it for our samples. Well, they have different samples, so it's the square root of n. So what am I going to put in each of these? What do you think? Well, for the blacks, I'll put in what? 84. And for the Hispanics, I'll put in what? Right there. 99. And that will be, so I have to work that out. Well, let's simplify it. So this is our numerator. I'll write it over here because it looks crazy over there. 1.795. And now, do you see what I can do here? I can pull out 3.18 because they have the same, right? And it's the square root of 3.18 squared. So if I take it outside the square root sign, this makes it super easy. This denominator will be 3, rather than squaring it and then square rooting it, I have 3.18 times the square root of 1 over the square root of 84 plus 1 over the square root of 99. That's very hard to see. So it's 3.8 times the square root of 1 over the square root of 84 plus, I just pulled that out, 1 over the square root of 99. All right? That's what that is. And when I did that, I did all that, I got this answer as, this is my t, 17.95 over that, and I got 3.804 as the t. Okay? Sorry that looks messy. So now what do I want to do? So I want to say how many degrees of freedom? Well, this is a t-test. So it just has one set of degrees of freedom corresponding. Usually it's n minus 1, right, for a t-test? But it depends on our error degrees of freedom right here. We're using this as the estimate. So the degrees of freedom are going to be n minus g, because I'm basing it on this standard deviation of the errors. I can get a much better estimate using all 858 points. So it's going to equal 858 minus 5, which is 853. That's the degrees of freedom for the test. And when I did that, I got a p equal to, we could do it, I have to, oh, here, I'll draw it right here. Okay, so I could do this t. Let's think about what we're doing. Okay, and we expect both as a t and as a actual difference, we expect 0 right in the middle. Okay, now I got this t of 3.804. And that turns out to be really, really far out on the curve. So between 3.088, between that and negative 3.804, it's going to be very similar to the normal curve because there's so many degrees of freedom. What I got, the p-value, is this tiny little area on both sides. Okay, because we're doing non-directional, and I got a p of 0.0152%. Now, I could just leave it there, and you'd think, why not? But here's where that ad hoc comes in, these post-ad hoc comparisons. Because there are 10 pairwise comparisons, and I cherry-picked out the one, there's 10 comparisons, and I picked out the one that I thought would have the greatest difference. I have to adjust this p-value and multiply it by that 10. All right? So it's called the Bonferroni correction. So I have to multiply it by what? Where did I get that? 5 times 4 divided by 2. That's what I'm doing. 5 times 4 divided by 2. And then I move the decimal place over 1. So it makes it 10 times bigger. So that is my p-value. It's called the Bonferroni correction. So that's my ultimate p-value. And you know what? I have a prettier, well, I guess that looks pretty good. But I think I have a nicer, from last semester, I just wrote it better. So I'm just going to put this here because I'm sorry. I think it looks prettier here. And I just didn't write as good this time. So there we have it. And it's the same exact thing, but maybe you can just read it better. That's called the Bonferroni corrected. Maybe you can just see this better at least. Okay? All right, so now, I know that was a lot. So does everybody have this copy down? Okay, so now let's just turn the page. And so look, this is all explained here on the next page. And you can see the, so I don't have to, I went through it, but you can see the standard, this is what we got, this is what we're using right here. This is what we used. And it would be the same if we did the z, it just would be, we wouldn't be using the plus errors. Okay? And here's the degrees of, so that's what we're doing. So it makes it super easy. And the degrees of freedom is the same as the denominator in the F-test. Why? Because we're basing it on the mean square error. the square root of the mean square error. All right, so now I want to show you what we did on the next page, so to make it easier for you guys to understand. So we were looking here, right here. We're doing this one. So let's focus on what we did. And first of all, you can ignore this chart. This is just for the z. We're focusing on this one for the t. And here we have the 10. Where does this come from? 5 times 4 divided by 2 is equal to 10 pairwise comparisons. Now, which ones did we look at? We looked at the difference in this average, 1.794. Is that what we got? That's what we did. 1.795 I got. This is just within rounding error. And here is our standard error for the percent. That's what we, standard error plus, and for the difference of these two. Not for the percent, excuse me. That's the standard error of the difference. If you looked at that denominator, that's what it boiled down to. What is this? Why don't I show you? So this right here is the standard error plus for the difference. This will make it easier for you to understand. So this is 3.18, right? That's our SD plus errors from the printout. And then we have the square root of what? 1 over 84 plus 1 over 99. And this was N for blacks. That's what that is. And this is N for Hispanics. So that's what this is. And what's that one right here? That was our difference. That's our observed difference, which was the blacks. It doesn't really matter which way we did it, but we got, because we're doing a two-sided test, but this was the average for the blacks minus the average for the Hispanics. That's where that comes from. Then when we divide them, we get that 3.804, which is what we got. This is our t. That's what we got on the previous page. And then we got that p-value, too. Now, we got that one. This is the Bonferroni corrected p-value. So these are the Bonferroni corrected p-values. They're multiplied by 10. You can see that because some of them are like 100%. You can't go over 100%, so if they went over, if you multiply it and go over. Okay? So we can, so the p-values are all multiplied by 10. Why? It's because we performed 10 tests and didn't specify which of the 10 we'd expect to be significant. All right? So that's really important. And if you want to look at the reasoning behind that, you can read this. And if you didn't do the correction on the next page, let's say you didn't do it. If we set our significance, this is actually good. You guys would appreciate this, because this is nice to look at, okay? So why do we have to adjust? All right, pretend we set our significance level at 5%. So you could see why this makes sense. What's the probability of getting at least one significance difference just by chance if the null was true and none of them were significant? So the probability of at least one significant result will be 1 minus the probability of no significant results, right? So that's 1 minus, now, what's the chance of the first result? No significant results. And then you say, so that's 1 minus, well, the chance of not getting a significant result is 95% chance that it wouldn't be significant, right? If we're cutting 5% as a significance, so it's 0.95 times 0.95 times 0.95 10 times, assuming they're independent. And that comes out to 0.4, or 40%. So with 10 comparisons, we have a 40% chance of making a type 1 error instead of the 5% that we want when we set the significance level equal to 5. So when you do this Bonferroni correction, what you're really doing is you're setting this, when you multiply by your p-value by 10, it's the same as dividing your significance level by 10, right? Instead of looking for, you multiply the significance level by 10, that's the same. You're multiplying your actual p-values, making them bigger. That's the same thing as setting your significance level 10 times smaller. So let's say we did that, and you do the same calculation, and now say, make it much, much harder to reject the null. Well, then when you do the calculation, you get about 5%. So, so that's why it works out. And this is the most conservative of all the tests because we're assuming independence. What does that mean? That means that if you're assuming that if one of the pairwise comparisons is not significant, that doesn't give you, or is significant, that doesn't give you any information about another one. Well, of course it does, probably, right? If you see one huge difference between, then that will probably give you some information about another pair being significant or not. So this is the most conservative test. There's a lot of other ones to deal with these post-hoc comparisons. Now, so the summary is really important. It explains it all. It explains what you do. Okay, there's basically two types of doing these hypotheses, and they all depend on when you state your hypothesis. We talked about this one, the post-hoc, which is the most common one. But what if we knew ahead of time, like next time I do this, I'm going to look for blacks versus Hispanics, and then I can state that ahead of time. Well, then I don't have to do any adjustment. If you specify your hypothesis ahead of time, you don't have to do that. You can just do the usual test without the same thing. You just don't multiply by the number of comparisons because you know more, and you state your hypothesis before you look at the data. So that's the whole idea. And next time we're going to look at the randomization method. Now your homework isn't posted yet. I'll post it later today.